What's up everyone? Welcome to another CS202 video. Today we're going to be exploring linked lists and they're really cool. It's a brand new data structure that you're going to be looking at. But before I tell you what they are, let me tell you what they're good for. So to do that, let's revisit arrays from CS135. So when you wanted to create an array, what you were trying to do was create a homogeneous data structure, right? And by that I'm saying that you had a list of a type, whether that be integers, floats, strings, or I guess 202 level, you can have class objects. And you had this list of data, and you go in and you throw it in a data structure, right? So you make an array. And it's nice because you can pick what size the array you want it to be, right? So like you go and say, I want to make an array of size 6, right? And so now you go and store some data in it. So you store a bunch of numbers. Now in 202, you sort of upgraded your ability to handle arrays by making dynamic variables, right? And with dynamic variables, what you're doing is you're able to create arrays on the fly, you're able to delete them, deallocate them, and make other ones. So if I say, hey, I like this array, it's really cool, but I want to add another number to it, what do? You make a bigger array, maybe one that has an extra spot in it, and you copy the data using that deep copy. I guess I made it the same size, but make it one size bigger. And you're good to go, right? Then you deallocate the old one and you have a new one that you can store a new piece of data, right? Okay, cool. What if I say, I want to insert a piece of data right in the middle? What do? Well, 202 knowledge, you allocate a brand new array that's one size bigger than that. And then as you copy the data over, you leave the space, right? So let's say you want to leave that space. And then deallocate the old one, basically. And then you have that space where you can insert, like, I don't know, number 9 or whatever, right? And so this has been your sort of basic approach to storing arrays of data. Now, what's the downside of this? The downside of this is that every time that you need to modify your array, whether that be to add elements or remove elements. Now, by remove, you could, of course, just like mark an element as removed, right? Like you could make this a little struct or class that has an extra spot in this class that shows you whether something's active or not. So let's just say we have a 1 for active and a 0 for not. And if something's not active, you can just swap it to 0. And now it skips that as it's counting, right? So you could remove things very easily. Adding things, whether that be at the end of the array or in the middle, is tricky because you have to make a brand new array, right? You got to make something bigger. Every time you make an array, you have, whether it's dynamic or not, you pick a size. So copying things over, it's a bit of a pain and it takes time. And that's not something that we really looked at the entire semester, aside from like kind of teased it on recursion. Like on recursion, we tease the idea that like you can't do infinite recursion because you stack overflow, right? So you get the idea that like some things you can't just do forever. But that's really as much as we've said in terms of time. When you get to 302, you're going to be just, time and space are going to be like your day and night. You're going to be exploring asymptotic complexity and all these wonderful things that are going to make you a better programmer, but also better understanding like why we do things the way we do them. For now, we're going to start to tease that by thinking about time and speed. And really those things are connected when it comes to computer because if something is slow, it takes longer time, right? And so I think most of us know the difference between a hard drive and an SSD, right? SSD is faster. We may not know why until you take CS219, or you can watch my videos from when I taught that. And you can see the real difference as to why SSDs are faster, right? But we know, just from a general concept that SSDs are faster. If I tell you, hey, I have two computers, same price, same specs, the only difference is this one has an SSD, both brand new, and this one has a hard drive, same size and everything. Which one do you buy? You should go for the SSD one. Now, the SSD technically has a shorter lifespan, but it's pretty insignificant. Like, it's not going to be that big of an issue. So you really should go with the SSD one. And so we know we like things to be fast. Well, guess what? This right here is like the hard drive. It's slow. And why is it slow? Because anytime I want to add things to it, I got to make a brand new one. I got to copy over all of that data. And then I can actually have space to insert something. And if I want to insert something again after that, well, I got to do the whole process all over again. Now, are there ways I can remedy this? Absolutely. I could make a massive array, like really, really massive, more than I needed. So let's say I'm only using this spot and the rest is massive. And then I can do this sort of same approach that I just showed you earlier, where like I can mark things as used and things as not used with zeros. This actually kind of teases a hard drive, because that's what they do, right? Like a hard drive, it's just, think of it like a massive array, like huge array. And then whatever's actually being used, you mark with as used, and what's not used, you just mark as not used with a zero. So kind of interesting connection there. Except this is not rounded, I guess. But yeah, so you could do that, but as you're adding things, you still need to shift things around if you want to insert right in the middle, right? Because like if you do this and you start inserting things, so like here you have 1, 2, 3, and you want to add more things, you already have the space, right? So you can just switch this to being used and then add things in. So you solve at least the issue of appending, right? But you still don't solve the issue of inserting, like particularly in the beginning, because you got to shift everything down. So, and also, even though you only shift or you only solve the issue of appending, you brought up another issue, and that is now you got to have this massive array that's being unused, at least in the beginning. That takes space. See? Space and time. That takes space. That space that you're using up in RAM, probably, that other programs can't use. So you sort of have this sort of conundrum, even if you're just thinking about appending. You can either make this massive array and just sort of fill it as you go and waste space when it's not being used. Or you can make an array that's the size that you need, and every single time you append, you gotta make a brand new one, which takes twice the space, at least temporarily, copy over from the old one, deallocate the new one, so now you've recovered that space, and then you're back to square one if you gotta add things again. Now, copying things over, you might be like, oh yeah, but that's fast, that's instant. Really, is it instant? Try copying a big file between even two SSDs. Like I'm talking about like 100 gigabyte file. Is it really instant? Because the last I checked, it's not, even with an NVMe. And forget about a hard drive. Like I used to back up videos that I would take with my cameras, like photography videos, and like even transferring like a 10 gigabyte file between like two hard drives is just excruciating. Like nowadays with SSDs it's nicer, but it's still not instant. Or with like an SD card. So yeah, even though this is all working in RAM, or at least it should be, it's still not instant. And when you're dealing with real world problems, you're dealing with real world size data sets, which are big. And so this ain't gonna cut it. This whole like, let me copy over, like imagine you have like a 100 like gigabyte file array, and you gotta like insert something in the middle. And you just like, you're like, hey, hold on a second. Let me just make a brand new 100 gigabyte array, copy over every single element, and then have that space so you can add that one more integer. And then do that again like 100 times throughout your program. That's not gonna cut it. It's gonna be slow. So what do? Well, in 2019, you're going to learn a bunch of other things you can kind of work around, like caches and all these fancy things to kind of hide the fact you're working hard behind the scenes. But there's a simpler way of sort of solving this problem, even in 202. And that is going to be your linked list solution. So right now, arrays are contiguous blocks of memory, whether they're dynamic or not. What that means is that when you ask memory, hey, can I have, or not memory, ask operating system like, hey, can memory give me like, a block of memory to store an array? It gives you a big contiguous block. Contiguous means that it's all together. That's a good thing for like pointer arithmetics, because you can immediately access any element of the array as long as you know its index. So if I want to access the 10th element of an array and I'm at memory 0, I know that I got to go to memory 9, right? That's the 10th element. Assuming you start from 0, right? Now, in real world, like memory could be like memory like 1095 or something. And you got to access some element from that. Just do pointer arithmetics and find out that shift, and then you immediately get there. It's instant. Well, instant doesn't like the time it takes you to do the math, like, what is 10 plus 10, 20 or something? That's the time it takes you to get there. There's no searching. There's no like looking around to find that spot, as long as it's in main memory. That's an advantage that we don't really think about, but it's there. Well, you don't really think about. You will when you get a trio too, all these things. But like, at least so far, you haven't really thought about it. You're just kind of like, yeah, arrays are there and they magically work, right? But there's a lot of stuff behind the scenes for that. And there's a lot of optimization in that sense because of the ability to have a contiguous block of memory. And when you make a brand new one and you copy things over, it's also a contiguous block of memory. That also is the reason why you can't just like insert something right there, because even in main memory it's all together, so you can't just like part the C's and just like put in an additional number in there. So because you can't do that, there has to be a way, somebody has to come up with some idea to like not have to deal with this massive blocks of memory, but and have an easier ability. Because like, if I'm sorting a deck of cards and I gotta put a card in between two cards, I don't need to like move all cards over. I can just like move them like this and then put the card inside and be good to go, right? So like, can't we do something similar as a way of storing data? And the answer is yes, we can. And that is thanks to the power of pointers. So, let me propose to you a brand new way of storing lists of information. Let's store 2 pieces of information per each block. The 2 pieces of information are going to be the following. We're going to have the data component. And the data component's job is going to be to store whatever we're trying to store. So whether that's a number, a string, an object, whatever you want. So you can think of that like this stuff right here. Now, this is where things are going to deviate from the array. We're going to store, and of course, because we have 2 components, we're going to do this with a struct or a class. But the second component we're going to store is going to be a pointer. And I'm going to conveniently call this pointer the link component. Now this pointer needs to have a type, right? You don't want to have boy pointers out there. So it's just going to be the type of whatever this class is called. So we're storing this in some struct or class. So I'm just going to give that a name. I did not come up with this name, but we're going to call it the node. Just a node, okay? Let's make more sense as to why in a second. We're going to call this class node. And this class node is going to have 2 elements, 2 member variables. It's going to have this data component, which is going to store the data per se, and this link component, which is going to be a pointer to another node, okay? So a node pointer. Not a string pointer, not an int pointer, but a node pointer, okay? And the data can be whatever you want. In fact, you can make it a templated variable. That way you can really store whatever you want, okay? So I'm going to represent this link with an arrow, because we know arrows, pointers, just kind of works, right? Okay. Now, what is this going to point to? Well, therein lies the rub. We're going to make a point to another node object. So we're going to make another one. Which is also, you know, it has its data component and it has its link component. And now this of course is stored somewhere in memory, right? And we're gonna make it dynamic. So we're gonna dynamically allocate this object. Let's just say it's in memory 11110, okay? That means that if this lives here, and then just to give this an address, we're gonna give this an address of 1221 or 120. What I'm going to do is I'm going to store this address here in the link component so that I can basically have it point there. And this is not something groundbreaking. You've done this before, tons of time. So that's what I'm going to actually store in the link component here. So I'm going to shrink this down and put it here. Now what is that doing? That's making this point to this, to the object, not just to the link, but like to the object. You can think of it to the beginning of the object, because remember how pointers work. They point to the beginning. Okay, that's really cool. What did this achieve? Well, you've just created a link between these two nodes. Go ahead and do that a couple of more times. What do you come up with? Let's try that out. So you have one connected to another one, and it looks like a little train. It's kind of like a little train that's going, right? They're all linked together. Well, this is a list. You can store information in your list. So let's go ahead and store 1, 2, 3, and 4. Guess what? This list in memory is not contiguous anymore, because as you saw, this is at address 1220 and this is at address 1110, right? These are hex. So they can be all over memory. They're no longer in an organized, contiguous, anything. So already there, that's going to be a bit of an issue, but I'll come back to that. The cool thing about this list that is linked, aka linked list, is that I can very easily add new entries to it. So suppose that I want to append something at the end. Dynamically create a new object of this node class. Bam, I've just created it. Okay, that's step 1. Step 2, store whatever information you want to store in it. So let's put a 5 in there. All right, in the data component. Step 3, take the pointer of the last item in your current linked list and make it point to this brand new object that you've made. So what am I talking about? Make this pointer point no longer to like some void here, which is actually null. Make it point to this. Voila. Even though it looks like this, I can redraw this to what it really is representing. Which is this right here. AKA, I just appended something without having to copy over the entire contents of the list. Already there is a big win. But we could have achieved this with arrays as long as we kind of made a bigger array than we needed to, right? The big one, the big question where we're going to see whether this linked list is useful is trying to insert something in the middle. Or what I would consider to be the worst case scenario for an array, which is inserting something right at the beginning. Because with the beginning, you have no choice but to shift every single element, right? If you're inserting in the middle, at least you know the beginning stuff is not being moved. You still got to make a brand new array. But like, let's say you still have, let's say you have an array that still has space at the end. You just got to shift things around. If you only had to shift half the list, then hey, at least it's half versus the full. But if you got to put in something right at the beginning, that's when you got to shift the whole thing, and it's just, it's bad. So let's see if we can do that here. Can we do that? Well, let me show you how we can. Yes, we can. So I'm going to go ahead and create a brand new node. Let's call this node 0 conveniently. And how do I put this at the beginning? Well, all I got to do is change this pointer. What am I going to change it with? Well, get the address of whatever this lives. This has some address in memory. Put that address inside of the new link component that you made. So you do something like this. And what is that going to represent once I redraw it here? Well, you can already see it. We have successfully accomplished this without having to delete or allocate anything else other than the brand new point that we just added, which is a 0. Hold on. I mean, the error looks kind of weird. So there you go. And just like that, I was able to insert something very quickly without having to copy an entire list, like do the whole deep copy, blah, blah, blah. So does this mean you should just like throw away all the arrays you've ever made? No, let's wait a second here. Everything has pros and cons. You're going to learn that very quickly in 302. There's pros to this, but there's also some cons that you may not initially be aware of. So yes, this linked list allows us to insert very quickly, at least compared to an array. It's like immediate. But there's a catch. There's a big catch, okay? The catch is the following. As you can see, I'm allocating these nodes throughout memory. And in reality, even though it represents this, which looks nice and continuous, it really does look like this. Or actually, a better representation is it looks something like this. Let me, this is what it really looks like in memory. So let's say this is the start. And then this like points here. And then this probably points here. And then that like points there. And then that also like points there. That's what it probably looks like in main memory. So, what impact does that have? Well, because we don't know where the next item is going to be, unlike arrays where it's literally going to be next to it. So you can just do like +4 if it's an integer and get the next entry on the index, the next index content. You can't do that here. The only way you can know where the next item in this linked list is stored, so where the next node is to look at that pointer. So like, let's say that you're here and you want to find out who's next. What do? Well, you got to follow the little pathway and get there, and now you can see it. That's not too bad because you have the address, so you can go immediately to the address here. So that's instant. But what do you want to look 2 spots ahead? Then you can't. You first have to go to the address that this says. So you first have to go here. And then once you're there, you can look at this address and then actually go there. So forget about trying to like jump to like the 10th item on the list. You're gonna have to literally, it's gonna be like a treasure map where like you gotta go to the next spot to get the clue for the next place. You're gonna have to do that here. You're gonna go visit every single entry between you and your objective to get there. There's no shortcut like the arrays where you can just jump right there. So because you only have a starting point, if you're trying to access that last element, you're gonna have to what is known as traverse the entire linked list by looking at all the pointers, dereferencing them, going to that memory address, getting it, and so on. Again, you haven't gotten to CS219, but computers are good at predicting what we're doing. So if you're accessing an array, and you're going like index 1, index 2, index 3, it catches on that and it preloads the other ones to be ready to go in the cache. When you throw in something like a linked list, there's no way it can know where the rest of the items are unless it actually dereferences them. And the computer doesn't really know that you're looking at a linked list. It just looks like you're accessing random pointers. So it has a negative effect when it comes to that because it can't preload things. Now, this is an oversimplification, but what I'm really just trying to get across is that yes, you have like you have gained great power when it comes to being able to insert things immediately to any part of this list. But the cost is that you can no longer access things immediately. So, pros and cons, time and space. With space, you basically have a super lean and mean list. You never have to waste more space than you have. Now, technically, each node has two entries. It has the data and then it has a link component. But that link component is pretty insignificant, especially if the data you're storing is more than just like an integer. You could be storing like a bunch of data. Because like you know, on a scale, it's really not going to matter. Like once you understand like asymptotic complexity, you'll find out that like something times 2 is irrelevant when you have another thing that is like squared. Like the growth rate of that is like insanely faster. That it does the 2 becomes like an extra thing. It's like a dot to the right, as they say. Okay? Dot to the right or dot to, yeah, dot to the right. Yeah. Okay. So, or no, a 0 to the right is the expression, right? I think that's what they said, 0 to the right. I don't know, whatever. You get the point. It becomes insignificant. So, basically, what I'm trying to kind of, in addition to showing you what linked lists are, I'm starting to make you kind of look at more than just whether a code does something or not. So it's no longer enough that your code accomplishes a task. We care about how much space it takes and also how much time it takes. And so now, if somebody comes to you with a problem and says, hey, I need you to store information for me, so you need to store a list. And this list is going to be something that once we make it, we never have to modify it. Already there, you should be citing towards having an array, because an array has immediate access time. You can access any part of the array immediately, and that's what you're aiming for. If on the other hand, they say, hey, we need to make a list of information that is going to be actively modified, as in we're going to keep inserting and removing things very often. We may still access it, but primarily there's a lot of insertion and removals. That's when you want to think about using a linked list, because that's going to improve that access, that insertion and deletion time. But there's going to be a cost to the access time. Now, is there a middle ground between these two? Well, linked lists and arrays are kind of extremes. When you get a trio 2 and you look at something like an AVL tree or a hash table, you'll find out that there are other solutions to this problem, but there's never going to be the perfect solution to the problem. So there's no one algorithm that is going to fit all problems. AVL trees are great, hash tables are great, but even they have their limitations. AVL trees, they're fast, but they're still going to be log of n time, which you'll learn what that means later on. Hash tables are good, but you have the risk of a collision, which is not a good thing. So, yeah. Okay, I have videos on that if you want to start peeking into 302 land. Otherwise, enjoy your time in 202, because this class is way easier than 302. So, yeah. Okay, so I think that's enough of an introduction into a linked list and to why it exists, why you should learn it, but more importantly, why you should start questioning more than like, you're no longer in the land of, can I do this? No, you got all, like I said a couple of weeks ago, you learn all the programming tools that you need now. Now we're learning concepts, because now we care more about not just whether you can do this or not, but how fast can you solve a problem, and also when you do solve that problem, is that solution going to be good enough? Is it fast enough? Is it going to not require an insane amount of space? Okay? So that's the name of the game now. It's no longer like, can I do this or not, but like, can I do it good or not? You're going to start to be judged not on whether you've completed a problem or not, but whether your solution is good enough or not. All right? It's like, hey, somebody asks you to build a car and you give them a bicycle and say, I mean, it'll get you there. It's just gonna take you like a long time to bike riding like 300 miles if you're trying to go to like LA or something. And they're gonna be like, yeah, no, it's summer, so not gonna work out. So yeah, now we're judging you on that too. So, yep, okay. So let's kind of let's just start coding a little bit. And I don't want to immediately code on a computer. I still want to keep things on paper. I guess we could code in the computer for a change. Yeah, I've done this a couple of semesters now. You can look at previous lectures. And previous lectures I like coded by hand a little bit. But I think this semester, let's just jump in the computer. Yeah. Keep it different, you know. So let's go ahead and just code a little linked list and go from there. Okay? Now, I want to make it templated because I want to show you that it doesn't really matter what the type of the data component is. You can be whatever you want it to be. And also it's a good review of using templates. So yeah, we're gonna make a template. So first, I'm going to go ahead and make a node, right? The node is the heart of the linked list. It's what stores the data and also the links that make it a linked list. Okay? So I could make this into a struct, but you know, keeping with the trend of using classes in CSS 202. And so really, like in the most basic sense, what you need to have is the two member variables. Like you could, I mean, I'm going to put in a couple of other things in here, but let's just start with the most basic. Okay, this is like your most basic version of a node class. You have the data component, which is going to store the piece of data. And again, I'm making it templated because I want to emphasize the point that this can be whatever you want, whether it be other objects in there. Heck, you could store linked lists inside of linked lists, like linked list inception. If you think that's overkill, I did that at one point as a final project for 202. It was called I think we just called it Inception assignment, and each reality from the movie was a linked list. So you had a linked list within a linked list. It was a pretty cool assignment, fun times. Maybe I'll bring it back someday. So yeah, this is the most basic of linked lists. However, I strongly encourage you to at least add one function to this linked list class, and that is going to be a constructor. Okay, now. Why is that? Remember, anytime you're dealing with pointers, you're probably going to end up crashing as you're coding this. And so you want to avoid crashing because you don't want to spend 2 hours like trying to debug and whatnot. So, I think I've said this enough times, but I'll say it one more time. Whenever you make a pointer, you should do one of two things. You should either initialize it to null, or you should immediately assign it to whatever it's supposed to point to. Don't just leave it hanging there with unknown data. Because remember, like no matter what like G++ does and shows as a 0, the C++ rules say that when you create a variable, it's uninitialized, which means that it can contain whatever was left there by a previous program, whether it's a pointer or not. And it's a danger because if you forget about that, and you think it has a 0 in it, or it's pointing to null or whatever, if it's a pointer, then bad things will happen. Because remember, the only way we can know if a pointer is valid or not is if it's pointing to null. That's how we usually keep track of pointers. So initialize it to null. You know, like save a pointer's life, initialize it to null. Okay. So I'm gonna make a constructor, and go ahead and in this constructor. I don't care how you do it. You can do it with this way. You can do it other ways. Initialize it to null. Okay? Null PTR. Null. Whichever one you want, just set it to null. Okay? Voila. That's it. Now, there's another thing you could do in here while we're at it. Might as well, since we could a constructor, and that is like I said, you want to initialize every variable you make, not just pointers. It's like maybe now we're getting greedy, but that's kind of the name of the game here. So let's also initialize data. Now, how can I initialize it if I don't know what it is? Well, I know, but you can pass it in as a parameter, right? So why not just like literally pass a parameter, call it D or whatever, and then in here, just literally set it to say something like data gets D, right? You could do it this way. You could also put it in here. Doesn't matter, whatever you want. Okay, I'm gonna go ahead and, for space reasons, I'm gonna leave it here like that because I can put this all in one line. But yeah, okay. Doing this guarantees you that whenever you make a node, it has to have a valid piece of information in it, to not to avoid a lot of headaches, and it's pointing to null. Now, why should it point to null? Because when you first make a node, you might not know where you want to put it. Like you might want to put it at the beginning, at the end, or whatever. You think of it like you're holding this little node. So you just want to make sure that while you figure out where you put it, it's not linked to anywhere, and that's why it's set to null. So that's a good thing. From like a visual perspective, when you're showing somebody like a linked list, this is just personal preference. I like to do the following. I put a little circle like that after the arrow, and to me this indicates null. Okay, that's just me, and the reason I'm telling you is because you might see me do that throughout the next few days as we talk about linked list. So just so you know where that came from. You're more than welcome to steal that. I probably didn't come up with it myself, so I just somewhere I picked it up. Have it. Okay, that's it. That's all you really need on this node. Now, you could go further. You could make like the data component dynamic, and then have a new and delete in there. But you'd have to have a destructor, copy constructor, and all those fancy things if you were, assignment operator overloading, all that stuff if you made it dynamic. So you're welcome to do that, but we're going to keep it simple by just doing it. Okay? So now that we have created a node class, let's just make our first ever link. Let's make two nodes and link them together. Okay? So let's just do that in main. So make a brand new node. The node should be dynamic, because at the end of the day, you want to be able to make nodes and remove them on the fly, right? Otherwise, why are you making a linked list? If all this stuff is known at compile time, make an array. Like, yeah. Oh, and by the way, quick pause here. I know someone's going to come back at me and say, hey, what about vectors? Like, I might have learned those, depending on what you took for 1 through 5, you might have learned about vectors. And then you might come back and say, oh, I can append things there and I can insert things there, and they're not linked lists. Hold on a second. Behind the scenes, vectors are doing that copying that you're seeing. So behind the scenes, vectors are still just dynamic arrays. And when you're inserting stuff in the middle, they got to make the entire copy. And yeah, so they have optimization, but they're still not like a linked lists. Okay, so yeah, so I want to see the vector comment. All right, so yeah, let's go ahead and make a node. Remember, with templates, we got to specify what it is. So let's just make 2 integer nodes. And then let's call those A and B. Or maybe node 1 and node 2. Nah, A and B is fine. However, these right now are not dynamic, so let's make them pointers. There we go. So now we got 2 pointers, or 2 node pointers per se. But they're not actual nodes, so let's just use the new call. So new node, right? And now, thanks to our constructor, it forces us to actually fill it in with whatever we want. So maybe we pass in a 2 on this one and a 3 on this one. Okay? So there we go. So now it's actually asking us to it's actually making a node and forcing us to define what is in it, and it's filling it with null. Because this is templated, I also need to put in the template type here. I think that's why that's being underlined. But let's try to run it. Okay, cool. It works. We got some memory leaks because we got the nodes. So maybe we should add a delete afterwards. So delete A and delete B afterwards. So now if we were to run this on Valgrind, we can see we have 3 allocations and 3 frees. Why is there 3? I only see 2. Okay, I won't question you, Valgrind. It probably includes who knows what in there. But we don't have memory leaks, which is what matters. So, yeah. Okay. So, yeah, so right now the nodes are just kind of existing by themselves. If I bring this iPad here like this, you can think of it like follows. We have a node A, and we have a node B. This is A, and this is B. You can think of it like A and B as being a pointer. So we have A and B pointer, A pointer, B pointer. And then this has a 2 and a 3, and right now they're both pointing to null. Okay? So what I want to do is I want to make A point to B. So I want to change this null pointer to point this way, right? So that it like physically looks like this, visually looks like this. All right, so let's go ahead and do that. So A's next, so remember A is the name of the pointer, so now I use the arrow operator. And I have access to 2 things, the data component and the next component. Hey, let's look at the data component for a second. So let's print that out. That should print us whatever the node's data contains, which is going to be a 2, right? Oh, sorry. I think I just recorded a video for my data analytics class on Python. So of course I was like, hey, let's call print. Wait, see out here. All right, so there it is. There's a 2. Here, I'll put it on its own line so you can see it better. But it's right. You can see it at the bottom there. There you go. Okay. So yeah, that is in there. And if I were to say B here, you would see a 3. Okay. So we know the data component is containing the data. But now what I want to do is I want to link them, right? So I want to link A to B. So I'm going to say A next, which is that pointer. Right now, if I also see out this, it should contain a null because of our constructor. You can see 0 for null. I'm going to go ahead and change that. Here, I'll leave that see out statement. Might be useful later. But I'm going to go ahead and change that to point by using the assignment operator to B. Like that. So now if I run it again, you'll see that I have an address in there. And that address is actually the address of B, right? This is pointer 101, like what we did a couple of weeks back. Think about how far we've come. Okay? What I've actually done, though, with this line of code is I've actually linked them, just like I have up here. How do I prove that to you? Well, let's try to use A to access the 3. How would I do that? Well, we know that A next is this pointer. So technically, once I'm there, I can just print out data, and that should print out the 3. And actually, while I'm at it, if I say A next, next, that can print out the pointer of B, which should contain null right now. But let's verify. So let's change this to say A next data, and then this one to say A next next. We can see that we are indeed accessing the 3 from A. See, that's pretty cool. And then next is giving us null. let's add another node and then throw it in at the end of this. So we have like a 2, 3, 4. So node int, we'll call this one C, or actually, you know what? Let's allocate this and throw it in immediately, because that's the thing. Right now, I mean, if we have pointers for every single node, we're not doing much. We could have done this with an array. The cool thing is to make a node and not have any reference to it other than the link itself from the previous node. So let's do that. We know that this is currently pointing to null. So in here, instead of assigning it to like point to something, which by the way, I could make it point to A. That's pretty cool actually. Let's do that. Just really fast. I mean, nothing happens like right now, but if I flip these lines around, you can see that now next has a pointer in it. What did I just do with that line of code? What I just did with that line of code is make a circle. And then this is actually pointing back to the 2. So I could go in circles forever. Check this out. If I go in here and change this to say cout next data, think for a second what is going to print out. What do you think? Is it going to print out 2, 3, a 0, an error? Prints out a 2. Why is that? Because 3's next is whatever follows after 3. And what's after 3? Because of the circle, this. So what if I change this from a next data to a next data? What's going to print then? If you guess a 3, then you are correct. That means we're basically going here to here to here. And I could go on forever. In fact, I could copy paste this like, oh, bam. Big copy paste time. And now I don't know what it's going to be, 2 or 3, because like, I don't know how many times I copy pasted. But hey, we got a 3. If I remove just any of these, doesn't matter which one I remove, but if I remove any of them, then I should get a 2. See that? Welcome to linked lists. So yeah, welcome to linked lists. Anyways, let's bring it back home a little bit. Just a next. Let's go ahead there and make a brand new node. So I'm going to say new node integer 4. So now that I got that, if I say a next data, then I should be accessing dot 4, as you can see right here, right? Because a next is B, and then a next is the equivalent of whatever's after B, which in this case is the 4, and then we're just getting that data, okay? So 4's data. We don't have a name for it, it's just some node's data. So what that physically looks like here is that. All right, time to actually do cool things, right? Let's try to remove the 3 from the equation here and make the 2 be linked to the 4. So, I mean, this is where we see the real power, right? To be able to insert or remove in the middle of it and whatnot. Actually, you know what? Before that, why don't we insert something in the beginning? That one's easy to do. Let's make a brand new node. And I need to have a pointer to it so I can store it somewhere. So I'm just going to use B. And let's get rid of the allocations for now, otherwise weird things are going to happen. So you might be thinking like, oh no, you're going to have a memory leak. Nah, don't worry. It's all good. We'll be fine. I mean, I currently have a memory leak because of that, but don't worry. We'll fix the memory leaks in a second. So yeah, I'm going to take this pointer that I have, so I don't need that actually. I can just do like B equals. And make a brand new node, and I'm going to call this node 1. New node 1. Yep, like that. And then this new node, I am going to link it to point to A, because that was my previous beginning, right? So now, if it's really pointing to A, that means that if I see out B data, that should give me a 1. And then I should also, if I do see out B like next data, that should give me a 2. So 1 and a 2 is what I'm looking for there at the bottom of whatever outputs. And that's what we get. Okay? So what does this currently look like? Let me try to draw it for you. So we have, let's start from the beginning. So we had an A and a B. So that was an A, and then we had the B. Pointers were pointing like that. And then we created that new one, which was merely created here, and this had a 2 and a 3 in it. And then we went ahead and created this on line 17. Okay, it has no pointer to it. How did we get there? We just did a next. So one next here and another next here to create this. Then I went ahead and changed B, so it's no longer pointing here. It's pointing to a brand new node that I've made. Okay? And this brand new node contains a 1. And then I said, okay, take that next pointer, so B next, so this one, and make it point to A, to whatever A is pointing to. What is A pointing to? To that. So that means that now this is pointing there, right? So if I redraw this to look easier to digest, then it looks like this. I'm trying to make it pretty for you. This was empty, but it has a 4 in it right there. And that's just null, okay? So that's what we have now. 1, 2, 3, 4. And then when I say something like B data, B is still pointing here. So now B is sort of like our link to the beginning of the list. And then A is just currently pointing here. So if I say B data, I'm getting a 1. And if I say B next data, then I'm getting a 2 because of that, which would be the same thing if I said A data at this point, which I can show you by just switching this to A. And then we should get a 2, 2 at the end here. Okay? So now let's go ahead and remove the 3 from the middle. Okay? Or actually, let's first remove the 2, because that one's easy to remove right now. Why do I say that? Well, because I have a pointer already to it, right? I have A. So if I want to remove the 2, all I gotta do is like deallocate it, right? Well, not quite. You're gonna have to move some links around, right? Like, remember, things are connected right now. So if I want to remove this and still have a working linked list, if I just like snap this out of existence, like Thanos style, then this is now pointing who knows where. Well, actually, no, it's pointing to wherever this is at. So remember, when you deallocate things or you remove them, like they're still there somewhere. So you have a dangling pointer. But worse yet, you lost this. That's a real memory leak. You have no way to access that. You lost it. It's like treasure map. It takes you from A to B to C to D. And if you lost one of those links, then the other clues are useless because you can't get there. So too bad. So we don't want to do that. We want to be very careful how we do this. And by that I'm saying, what I want to do is I want to take this pointer, which is currently pointing to 3, and want to copy that over to 1. Why do I want to do that? Because when I do that, what I'm going to end up doing is I'm going to end up having this point here. So now, when I delete this, I still have my links working. And this is, you know, this looks okay now. It might look squiggly, but this is good. All right. So you have to, you got to tweak it. You got to tweak the pointer from the one before it. Okay. This is where most people kind of get stuck with linked lists, is when they start, you got to start updating the links between them to remove and add. But the best thing I can recommend to you is do what I just did. Do it on paper. Make sure you're updating the things as you expect, and that's how you solve most of the issues from creeping in. So let's go ahead and do that. So let's take A. Next, which is currently here, let's backtrack so we can see what this looks like. There we go. So this is what we have. Well, one more time. Yeah, this is what we have. So I want to take the link to 3 and copy that into 1. So I have 2 ways I can do that. The easy way is I have A right now, and A next contains that link. So I want to copy this link into B's next. Once I do that, then I've created that arch over. And now I can safely remove 2. How do I remove 2? Well, very easily. Just call delete on B, right? Or sorry, on A, because that's what A is currently pointing to. However, this is kind of made easy because we have this A pointer. Suppose we didn't have the A pointer. Suppose we erase that, or we're not using it. Can we still do this? Yes, we can, because we have B. What we got to change now is here, I can say B next is going to get whatever B next has, right? Because B next is the same thing as A next. B next gets you here, and then B next gets you to the 3. So that's one other way that we can copy over that. And we don't have to use A at all. However, if we do this, we do run into an issue. And that is, now that we've made the link, that's the equivalent of doing this. But guess what now? Sure, our linked list now says 1, 3, 4. But I lost access to 2 now. Because we're imagining we don't have this A. It's not have a memory leak. Not a good thing, right? So what do I need to do to avoid that? Well, you're always going to need an extra pointer to temporarily keep track of that so that you can then deallocate it. Now, you could say, oh, well, I can solve this easily. I can just like put in a delete here like this. Delete B next, the old next, right? Which is this one. Delete B next. And then update it this way. But then this is technically accessing a dangling pointer because you're accessing something you've deleted. So that's not a good thing to do. So the best thing to do is to essentially use a temporary pointer, which in this case can be A. A is already pointing there, but think of it like our temporary pointer. And then go ahead and do your arch link and then go ahead and delete it. Okay? So let's go ahead and repeat the process now. So now what we have left after doing that delete is the following. We have 1, 3, and 4. Let's verify that we have that, okay? So cout A, B is the one that's at the front, so B data. And here, I don't like dangling pointers, so I'm gonna set A to null after that. Okay. All right, so that's the first one. And then let's get the second one in there. So B next. Like that. Okay, so we can see we have 1, 3, and 4. Very good. Where's the other cout coming from? I don't know. Let's just say current. Okay, so now let's go ahead and remove the 3. Let's remove the 3 from this. And all we really have is our B. We don't have any A and whatnot, so we're definitely gonna have to do this. We'll do it the same way. Step 1, I get a pointer to what you want to delete. So in this case, we can use A, because A is currently pointing to null. So we're gonna make A point to whatever we want to delete. So in this case, it's gonna be B next. Step 2, go ahead and update the pointer. So make the arch. So go ahead. Now that we have this, make that arch. 2 ways you can do this. You could either say B next gets B next next, or you could just say B next gets A next, right? Because A next is the same thing as B next, so you could substitute it in essentially. But we're going to stick with the first one. Actually, we'll leave the second one in as a comment. Okay, once I do that, then all that remains is to go ahead and delete A and then get rid of dangling pointers, so set it to null. Okay? Once you do that, then let's go ahead and reprint what we currently have in the linked list, which should be 2 things. As you can see by 1, 4, right? Because we deleted the 3. All right, we're pretty much done now, so let's just go ahead and deallocate what we have left, so we don't have memory leaks. So let's just go ahead and deallocate. Again, we don't want to delete B and then delete B next because that's a dangling pointer. So you want to make sure that you flip these around like such. And so now if I run this, with Valgrind, you will see that I have no memory leaks or errors. Okay, so that is the basics of manipulating nodes within the linked list. Obviously, this is a mess right now. Like, basically, what I'm doing is I am creating a bunch of nodes and adding them and removing them on the fly. It's messy. It's just messy. There's no other way to describe it. What I want to do now, though, is I want to make a class called linked list that does this automatically, right? So like whenever I want to insert something into my array, I can just, I'll just go into programming. I can just call a function that can insert to my array. If I want to remove something, or linked list. If I want to remove something, I can just call the remove function. I can create an append function. Like my insert can say I want to insert on the 5th spot. Or maybe I want to make a sorted list, and then it inserts in the right spot depending on where it's sorted. So I can do all of these functions, but at the end of the day, this is what you're doing. You're doing this manipulation of pointers and allocations and deallocations of these nodes, depending on if you're adding or removing them. So it's important to know the basics before you go out there and create like a linked list class. Also, I want you to notice a disadvantage of our linked list. If you try to print it reverse, you can't really do that because the links are going in one direction, right? So if I want to like print something backwards, I can't. I either need to use recursion, which I could, and that's actually a pretty cool way of using recursion, or I need to have pointers in both directions. That does exist, and it's called a doubly linked list, and we will explore it once we finish looking at a singly linked list. But I wanted to just make you aware that that is out there. It's convenient because you can go in both directions, but it technically has the additional cost of having one extra pointer to deal with for each node, which means when you're adding things, you got to update basically multiple pointers now. Well, not just one more pointer you got to update, I suppose. Well, on each side, I guess. Yeah, on each side. So you got to update 2 more pointers instead of 1. So, that sucks, I suppose. Not 2, 3 technically, because I guess you got this one for 2 nodes. Yeah, I guess 4. But yeah, we'll explore that when we get there. So debating if I should call it a day on that. I'll tell you one more piece of terminologies, and then we'll call it, because the next video I want it to be, might be a little longer, but I want it to be the full video where I make the linked list class, which is going to be the big thing. So yeah, let me just tell you two more pieces of terminology that you should be aware of on a linked list. So you already know the node, what that means, which is each of these little boxes here. You know what the link component is, you know what the data component is. This link component is typically called next or link. Like, that's just the typical names. I like to use next. There's also a very important pointer that should have on, oh, hold on, I need to switch over to this. So you got your link components, which are these, which are also called next or link. You saw me use next today. And then you have your data components, right? Which I think I've never heard them call anything but data, but who knows? There's also two more things that are sort of important to know, and that is, you always need a pointer that points to the beginning of your linked list. That's how you start accessing it. I was using B and A here throughout, but there's an official name for that, and that is known as the head pointer. And that pointer is going to be of your node type, okay? So what are the name of the classes here? It's going to be basically identical to these pointers, okay? It's going to be identical to those, like, I mean the same type. And that head component should always point to the first item. If you insert something to the beginning of a linked list, you should update that head component. I'll show you how to do that when we code it in. This is the minimum requirement to have, although it is also convenient to have another pointer at the end of the linked list, which is known as the tail pointer, okay, or tail component. Also a node type pointer, very useful when you're trying to just add things to the end of the list, because remember, if I want to put something at the end of a linked list, I got to traverse the full list to be able to append. Not very efficient, kind of defeats the purpose. By having a tail pointer, you can just look there and tail next, put it there, and then make sure you update your tail, just like the head. When you add or remove things, you gotta make sure you update them. And so that puts you in a good spot. The disadvantage is going to be, if we go back to what we were talking at the beginning of our class, is inserting in the middle of this list is the worst case scenario, because you have to traverse to that spot by dereferencing the pointers, and then you can insert. So the actual insertion process is super fast because you don't have to copy things over. But getting to that spot is where you lose that speed. So does that mean that like linked lists are kind of like not the best thing ever? Not quite. You'll see that when I show you a queue and a stack the last week of the semester, a linked list is still like awesome for this stuff because it allows you to grow it and shrink it without problems. So yes, the dog is pressuring me to feed it. It's time to eat, I guess. So yeah, that's the two terminologies that I wanted to make sure that you were aware of. We'll revisit these as we create a linked list class on the next video. So with that, I think I'll wrap up. So I thank you all for watching. I hope that this has given you a good introduction into linked lists. And like I said, for the next couple of days, we're just going to be coding linked lists. I have done this previous semesters. Sometimes I make mistakes and the thing doesn't compile or crashes. Last semester I was pretty lucky. I got it all working on the first try. Live. That was a live one. So we'll see how we do around this time. But the reason I bring this up is because you can go and watch those videos too if you want to see more examples of me coding linked lists, because they're always a little bit different. Last time I didn't make it templated, if I recall, so I think this time I'll make them templated. So, or maybe I did, I don't remember. I'll try to check, because if I made it templated, maybe this time around I won't make it, just so you have more examples. So yeah, check those out too. All right. Thank you for watching. I'll see you next time. Peace out.